Welcome back, everyone. This is example 11.9 in your notes, and this is uniform circular motion, and we're going through a couple examples right here. And this one's kind of cool because we have a we have an object being spun around in a circle, and a centripetal force being created on that object. In this case, it's a puck, and it's being balanced out by the force of tension of an object that's being pulled towards the center. And hopefully, if we get a chance to, we'll actually be able to do a lab like this year, where we'll see how this tension of this object dropping down is balancing out the outward pull of the object moving around in a circle right there. But I'm getting ahead of myself. Let's start properly labeling this. Well, what's the question? The question is what speed or what velocity. Okay, now the last question said what speed in RPM. Speed is kind of a generic term. We should really clarify that. But this I'm going to take to mean what speed in velocity or tangential velocity does the puck need to slide at to keep the cylinder at rest. Okay, now a couple things make this a little bit easier for us. Number one, it's a frictionless table, so we don't need to worry about friction. All right, the mass of the puck, lowercase m, is 1.5 kilograms, and the radius equals 20 centimeters. All right, well, that needs to be converted to meters, so 0.20 meters. And the mass, capital M, of that weight right there hanging down through the middle of the table, that is what? 2.5 kilograms. 2.5 kilograms. And we want to find what the velocity, the tangential velocity is of that puck. Okay, now I'm going to go back and actually start marking up this little diagram right here. So these two forces have to be in balance with each other. This downward force and this tension force right here. Why? Well, because the cylinder needs to stay at rest. The cylinder can't move down, so the tendency of that to be pulled down by gravity, capital M, not a good capital M, G, has to be balanced out by the centripetal force created by this puck spinning around in a circle right there. So we're going to say that, I'll write it over here. Capital MG is going to be equal to the centripetal force, or I should really say the net centripetal force, because there's no friction or anything, so we don't need to worry about that. But that's going to be the net centripetal force caused by that puck right there. Well, we turn this around here. Net centripetal force. We know capital M, and we know what G is, so that would be 2.5 kilograms times 9.81 meters per second squared. And so our centripetal force that must exist in this puck spinning around is going to be 24.5 newtons. Okay. So we know now the centripetal force, what this must be right there of the puck spinning around. Well, we want to know what the velocity is of that puck. Well, so let's write out what we know about centripetal force. We know centripetal force is mass of that object. In this case, it's the puck, so lowercase m, times acceleration, or centripetal acceleration. F is equal to ma, that's Newton's second law. And we want to find velocity, remember? So we could do this in a couple different steps, or we could simply break it down further. how can we state centripetal acceleration in terms of velocity? Well, we can say that, put that in brackets there. If you recall, centripetal acceleration is velocity squared over the radius, right? That was probably our first equation for centripetal acceleration. So if we know that to be true, why don't we solve for our velocity simply by comparing it to the centripetal force? Centripetal force is the mass of the puck times the velocity squared over the radius. All right, let's solve for velocity. Let's do velocity squared first. That would be F, our centripetal force, times R divided by the mass. So that means the velocity must be the square root of our centripetal force times the radius over the mass. Nothing more than plug and chug now. Our centripetal force we found out up here to be 24.5 newtons. Our radius, what's that? That's our given, right? It's one of our givens. 0.20 meters divided by the mass. In this case, it's the mass of the puck, because that's the thing that's spinning around in a circle. That's balancing out the weight in the middle. That's divided by 1.5 kilograms. And I get 1.81 meters per second. That's it. That's example 11.9. Now again, that comes from the fact that we set the weight of the object in the middle equal to the centripetal force of the object spinning around. They're equal, if they're equal, that means that the cylinder won't slide down or it won't come up. That it's perfectly balanced with the centripetal force of the spinning puck. So that's the supposition that we started with here. The rest of it was all just simply using equations that we've known from our notes. So there you have it, example 11.9. Let me know if you have any questions, and I'll see you in class.